All right, so thank you all for joining. We're picking up after a few weeks of not having any seminars. We're picking up our applied PD seminar at the University of Washington again. I'm delighted to introduce Stephanie Dodson, our speaker this week. Stephanie is currently the Greener, I hope I'm pronouncing it right, assistant professor at UC Davis. I believe she got to UC Davis directly after her PhD, which she obtained from Brown University under the direction of Bjorn Sandstede. Stephanie works on a lot of different things related to spatiotemporal patterns, and a lot of those are related to do with some biological applications, including the one she'll talk about today, one-dimensional spiral waves and reflection-induced cardiac arrhythmia. Stephanie, thank you very much.
Yes, thank you for that introduction, and thank you for having me be here today. So today I'm excited to tell you about what I've been working on for the last year and a half that I've been here at UC Davis. And this work that I'll talk about today is joint with Tim Lewis, who is also here at UC Davis. All right. So a lot of the motivation for this work comes from understanding the formation of cardiac arrhythmias. So in normal cardiac tissue, so this picture on the left is just a slab of cardiac tissue. During normal heart operation, normal heart function, what we would have is this nice planar wave passing across the heart tissue of electrical activity and causing the heart to excite and contract uniformly. This then allows the blood to pump throughout the body. However, during abnormal behavior or arrhythmic behavior, we get these irregular waveforms on the heart surface. And these irregular waveforms can include things like these rotating spiral waves and other chaotic activity that this video is eventually going to become into. But there's a big gap missing here in the middle. So how do we actually get from this normal operation into this arrhythmic rhythms? And so one of these mechanisms that's been thought to generate arrhythmias is through wave reflection. And so this is the mechanism that we're trying to understand. And so in this video, you can again picture it as a slab of cardiac tissue. What you're going to see is in red, a wave that passes from left to right, and it's going to interact with an invisible heterogeneity here in the center. And as it interacts, you're going to see that that wave reflects backwards and then generates a pair of spiral waves. So there's that reflection and generates this pair of spiral waves. So again, let me play that again. Our purpose is to try and understand what more about this reflection mechanism in order to help stop the formation of these arrhythmic rhythms. And so what we're going to do is consider reflection as a purely 1D phenomenon, because if you saw during that time of reflection, it's really, you can think about it as a one-dimensional phenomenon. And so I also want to
ask a question.
Yes, go ahead.
The video you just showed, is that numerical or is that experiment?
That is a numerical simulation.
Okay. And so you're showing a small window of a larger computational domain?
I believe that this one was actually, this is the full computational domain here. But yes, this was the full computational domain for this simulation.
Okay, thank you.
Yep. So I want to point out also that these reflections, they have been observed both experimentally and numerically before. So they've been observed experimentally in Purkinje fibers, which are in the ventricles in the heart. They've also been observed in ventricular and atrial tissue. And they've also been observed in computational models, both from a continuous standpoint, from like a PDE standpoint, and in network models as well. And so we're going to be focusing on these reflections as this 1D process. And so I want to describe a little bit more about the phenomenon that we're going to talk about. So in what I'm going to show you, we're going to consider a 2-variable PDE model where this is going to be our voltage variable and green is our recovery. And so what we're going to have is this traveling pulse that's going to interact with a refractory bump. And so this refractory bump is just an elevated region of this recovery variable ahead of the wave. And so in this case, this refractory bump, it's going to act as a type of functional heterogeneity. So you can think about it, there's nothing structurally wrong with the tissue there. It's just some leftover refractory region. And so we're going to say that the height of this refractory bump is going to be capital B. And so if this amplitude is relatively low, what we're going to see is that the pulses will interact with it, but it'll eventually make its way through. So what I'm showing you here are space-time plots of that interaction. So the refractory bump, you can kind of see it, it's this darker region just ahead of the pulse initially. So if the amplitude is relatively low, we have this short interaction, but it goes back to its original behavior. If the bump is large enough, we can actually get that the pulse is fully blocked and all the activity afterwards ceases. However, as we tune this, the amplitude of that bump, we can actually get more complicated behavior, and we can get these reflections. So here we have just a single reflection, but as we tune this parameter B towards this critical value, we can see that we can actually initiate this more successive train of reflections. And so I want to point out that for these two that have multiple reflections in it, we're not introducing more refractory bumps. The only refractory bump is at the beginning that's causing this initial reflection. After that, we're seeing this spontaneous series of reflections arise in. And so this phenomenon was observed earlier on, and it was actually investigated by Ehrmantraut and Rinzel in 1996. And so what they did is a similar experiment where they had a pulse traveling on a 1D cable. And what they had was a structural heterogeneity that was the cable width changed at a certain point. So instead of having a refractory bump, they had a changing width of the cable. And they observed the exact same behavior. Whereas if the diameter, that D of that thicker cable, if it was small enough, you could have the pulse that propagated through. If it was too large, the pulse would be blocked. And in the middle, they could see the subsequent series of reflections. And as you tuned the diameter finer and finer, you could get more and more of these reflections. And so this behavior led them to hypothesize that reflections are driven as the system is actually approaching an unstable periodic orbit. And the closer you tune your parameter to bring you near that periodic orbit, the more of these spontaneous reflections you're going to get. And so in this system, that diameter of the cable was that parameter to tune, whereas when what we just looked at, the amplitude of that refractory bump allowed the system to approach this unstable periodic orbit. So Ehrmantraut and Rinzel also linked that the unstable periodic orbit was actually what was dubbed by Coppell and Howard this 1D spiral wave. And so this is what we're going to be looking at today, this 1D spiral wave. And so this 1D spiral wave takes the spatiotemporal form that we're seeing in this diagram here. And so you can think about it as this infinite series of spontaneous reflections. So here we see that at the core region, there are these reflections that are happening. And I want to emphasize again, there's nothing that's generating these reflections to happen. There's no structural or functional heterogeneity in this diagram. And we're going to have it's infinite, so picture this continuing infinitely in time as well. And so if we were to take one time slice in space, what we would really see is periodic wave trains emerging from either side of this core and arranging into these regular structures in the far field. So where does this name, the 1D spiral wave, come from? Well, it comes from the fact that if you were to take a radial cross-section of one of these 2D spiral waves, you would see a similar behavior as I'm showing in this middle diagram. So that's why it was dubbed a 1D spiral wave. And so I want to be clear on the notation here that today I'm not talking about these 2D spiral waves. The 1D spiral wave, it's related mostly by name, but today we're purely focusing on this 1D spiral wave case. And so really the idea that we're working with and the idea that Ehrmantraut and Rinzel proposed is that the ability for waves to reflect really depends on the existence of this 1D spiral wave. And so even though this 1D spiral wave is an unstable periodic orbit, the existence of this periodic orbit still controls the possible dynamics that you have. Because if the system approaches that periodic orbit close enough, you can generate this series of reflections or even just one reflection. And so for our case, for this application to cardiac arrhythmias, we don't necessarily care that you can generate an infinite series of reflections. What we really care about is the probability of generating at least one reflection, because then it could initiate this arrhythmic behavior. So this question about these reflections was studied again by Citron, Baum, and Lewis in 2009. And they studied this in the Morris-Thakar model. and found that reflections were possible under some conditions. And so they did a similar numerical experiment where they had a traveling pulse in the Morse of the car, and they initiated that traveling pulse with a square wave or with a smoothed out square wave. And here what they did was they, for their bifurcation parameter, tuned the amplitude of that initial condition. And so it's known in the Morse of the car system that there are a few different possible solutions, including a pair of fast and slow pulses that are created at a saddle node bifurcation, and also the homogeneous rest state. Well, what Citrin-Baum and Lewis found is that if they fix a value of this parameter epsilon, I'll get to more about this later, but if they fix a value of that near that saddle node bifurcation, no matter what amplitude of the initial condition they started with, they would not see reflections. So if you start with an amplitude that's above that of the fast pulse, you would see it very quickly converge to the fast pulse, which is stable. Again, if you start below it, it would converge to the fast pulse. Whereas if you start below the amplitude of the slow pulse, it would converge to that rest state. So no matter in this case what amplitude you pick, you're not going to get a reflection seen. And so in this case, the slow pulse really acts as the boundary of the basin of attraction between these two stable states. However, what they found is that if you decrease that epsilon small enough, you can actually get these reflections. So if you're to choose an epsilon less than this value, I'm going to call it epsilon star, and do that same experiment by changing the amplitudes, you can actually see that these reflection behaviors do emerge. And so again, in this case, there's no structural or functional heterogeneity. All we're doing is tuning the amplitude of that initial condition and finding these reflection behaviors. And so Citrin-Baum and Lewis, what they did was they did some numerical simulations and investigations and determined that this 1D spiral wave, it seemed to be linked to the slow pulse. And in some sense, it seemed to almost bifurcate from the slow pulse. Because if we look at what's happening at the core of these reflections, these kind of thinner portions here and lower amplitude portions, those are actually very similar to a slow pulse. And so it looks like the slow pulse, there's a bifurcation from it that's causing this reflection. And so they did some studies and they looked at what happens to the period of the 1D spiral as this epsilon approaches this epsilon star. And they hypothesized that this 1D spiral actually appears through a heteroclinic bifurcation related to the unstable manifold of the slow pulse. And they also did some additional computations to find that the slow pulse itself is not changing its spectral stability at all. So this led them to really believe that the 1D spiral is created through this heteroclinic bifurcation. And so there are still a lot of open questions. And so again, kind of the hypothesis that we're working with and the assumptions we're working with are that the ability for waves to reflect is really linked to the existence of this 1D spiral wave. And so the key questions that we want to answer are, how do system conditions influence the likelihood of reflections? So ideally for our application, we'd like to be able to remove these reflections completely, because if we could remove reflections, then we could remove these reflection-mediated cardiac arrhythmias. And so we're actually going to break this likelihood of reflections question into two parts. The first being, can we actually make the reflections not exist anymore? And so that is going to be understanding the existence of this 1D spiral and understanding if the existence, how that's based on system conditions. So can we change some parameters and actually make it so that this epsilon star moves far to the left so that it's not really a problem anymore? The second question is going to be, well, if we can't move the location of that bifurcation point, can we make it so that reflections don't occur as frequently? So we're going to ask, how does the probability of reflections occurring, how is that based on system conditions if the reflections do in fact exist? And so along the way, we're also going to ask and find out more information about what is the dynamical mechanism and bifurcation that leads to the formation of these 1D spirals. And so the outline of this talk is going to be set up to address these questions. So I'm first going to talk a little bit more about the mathematical setting, talk more about where these 1D spirals come from, and then go into answering these two questions about the existence and parameter-dependent likelihood of reflections occurring. All right, so getting into the mathematical framework. So I first want to talk a little bit about the electrophysiology of Morse the car and what types of processes it's capturing, because we're going to be changing some of these parameters to see how the conditions influence the likelihood of reflections. So let's first consider the Morse the car in a single cell. So I have the Morse car shown here. It is a system of two equations where the equation V represents the voltage, and N tells you the proportion of actin potassium gates. And so the voltage V has three currents in it. It has the calcium current, potassium current, and a leak current. And these three currents are responsible for the action potentials. So the calcium current is responsible for depolarizing the cell, and the potassium current is responsible for the repolarization process of the cell. For the N equation, the proportion of active potassium gates, we have this written in the form of the activation and deactivation. So alpha is our activation function and beta is our deactivation function. So that parameter epsilon that I was telling you about before, that appears out front in the N equation. And so that captures the excitability of the tissue and also controls the time scale of that recovery process. So the other parameters that we're going to be interested in are these maximal conductances, the GCA and the GK. So they essentially dictate this maximum strength of these two currents. And we're also going to be looking at these parameters U3A and U3B, U4A and U4B that appear in these activation and deactivation functions. And so the 3A and 3B, what they do are they act to shift those activation and deactivation curves, whereas 4A and 4B, they act to scale them. So I'll revisit this slide once we go to interpret the results, but I just want to give you a little bit of insight about what these parameters that we're doing, that we're going to be changing, actually do in the system. All right, so what we're going to be doing is looking at the Morse the car in 1D in space. And so to do that, we add a diffusive coupling term into the voltage equation only. But we can think about this as our general reaction diffusion framework. And so in the Morse the car system, there are known to be two pulse solutions. There's a fast pulse and a slow pulse with their speeds of propagation dually faster and slower. And so these pulse solutions, they are known to be created at a saddle node bifurcation that I'm going to call epsilon saddle node throughout. And we also have this stable homogeneous state throughout as well. But these pulse solutions, we can consider them in their co-moving frames with the respective speeds, and then we can compute them as equilibrium solutions numerically. In the system, we also have periodic wave trains, where the wave number kappa and the frequency omega are controlled by a dispersion relation. And again, in the correct moving frame of phi, which ends up being 2 pi periodic, we can compute these again as stationary solutions. So these two 1D structures are going to be some of the building blocks that we're going to need in our investigation. All right, so we saw then, Stitch, Bob, and Lewis saw that as you decrease the value of epsilon below that critical value epsilon star, you saw the appearance of this 1D spiral wave. And so they also believed that this 1D spiral wave arises through this heteroclinic bifurcation. And so some of the things that led them to believe this are they did some computations using shooting methods and found out that as you approach this epsilon star from below, you can see that the period of this 1D spiral is growing. And it turns out that it's growing, appears to be growing exponentially. So they did these computations that involved shooting methods to find this unstable 1D spiral. However, these methods are not super efficient, particularly for finding these unstable structure. So one of our goals is that we're going to be using more precise numerical methods to be able to efficiently compute and understand this unstable structure. So we're going to consider this 1D spiral as this two-dimensional spatiotemporal pattern. And so at the center or the core of this pattern, it's really the slow pulse that's connecting these oppositely propagating waves. And so it's really like the slow pulse is propagating in time and then shoots off a fast pulse the same direction and a retrograde slow pulse. If we were to look at the far fields away from this core of this pattern, we see that the waves assemble into this nice periodic wave train and into this regular structure. So we can then think of this 1D spiral in space as a heteroclinic connection between those two periodic orbits that are the periodic wave trains on either side. You can also think about it in time as this periodic orbit as well. And so you can also think about this as being an antisymmetric source defect. It is a defect because as you're to travel in space from one side to the other, you're going to see this abrupt change in the wave number at that core region. And it's actually that defect in the center that selects uniquely the far field wave number and the frequency. And so it's a source defect because if you're to compute the group velocities on either side of the core, they're going to be pointed away from it. And so we're going to use this structure to really help us compute these spiral waves. And so again, we're treating it as a two-dimensional pattern in time and space, and we're going to treat time as essentially a periodic spatial variable. And so what we're going to do is rescale our time by the frequency omega so that it can be 2 pi periodic. And then what we can do is take our reaction diffusion equation and be able to rewrite it as an equilibrium solution. And so that this 1D spiral is the equilibrium solution to this equation. And so in order to compute this efficiently, what we're going to actually do is decompose our solution. And we're going to use the structure to do that. So at the center, we have this core region, and on the ends, we have these regular patterns in the far field. And so what we're going to do is write our defect solution as equal to the core plus the regular periodic wave trains in the far field, and they're going to be connected by a smooth cutoff function, this chi. And so what we can do then is compute this far field pattern, pre-compute it just using the 1D periodic wave trains and interpolating them into this two-dimensional space. And so then the only thing that we actually have to solve for is this core region, which is localized and therefore is going to be much more efficient to compute than the whole pattern itself. So some of the benefits of doing it this way are that we are going to get faster convergence. Computing the 1D spiral as a spatiotemporal pattern or as an equilibrium solution, this is going to give us an advantage over some of those shooting methods because we'll be able to compute this unstable pattern efficiently, and we'll be able to find out information about it, such as its wave number, its frequency, and we'll also be able to continue it in other parameters. Furthermore, since it's an equilibrium solution, we'll be able to actually compute its spectral stability as well. All right, so now I want to get into understanding the existence of this 1D spiral. So asking the question of what are the dynamical mechanisms that lead to the 1D spiral, and then how does the 1D spiral existence depend on the system conditions? So first I'm going to go through the proposed structure of this heteroclinic bifurcation. And so this is from that Citron-Baum and Lewis paper in 2009. So what we're showing here is for values of epsilon much greater than that epsilon star. So this is the conditions where the 1D spiral does not exist. And so in here, what we're showing in R, this is our rest state. The F's and S's, they are fast and slow pulses, with lowercase meaning it's moving to the right and uppercase meaning it's moving to the left. Sorry, I flipped that. Lowercase moving to the right, lowercase moving to the left, uppercase moving to the right. These red arrows, they are the unstable manifold of the slow pulse, whereas the blue dashed are the stable manifold. Any of these patterns that have this hollow triangle, they're going to be unstable, whereas the solid circles and squares are stable. So for example, if we were to take this FSF here, we would have one fast pulse moving to the left and a slow and a fast pulse both moving to the right in that order. And so what I want you to look at as we advance these slides is what happens to the unstable manifold of that slow pulse. So as we approach epsilon from the right, what happens is that the unstable manifold of the slow pulse, it's going to start to bend and move towards that SF solution. So over here, it's just connected to the fast pulse, but it's going to start to bend. And then as we get to that epsilon star, that critical value, what happens is that this heteroclinic connection actually breaks, and instead of being connected to the fast pulse, is now directly connected to that slow, oppositely propagating slow fast pulse. And so you can see that on the top here, we just have like the slow and the fast pulse in the rest state, and below it, we have all these different series of pulses. And so it's hypothesized that not only is this top connection breaking, but anytime there is a slow pulse in one of these series, those connections are breaking as well. And so you can see that happening all down this line. So then when we move below epsilon star, now that unstable manifold of the slow pulse, instead of connecting to that slow fast pair, it connects to oppositely propagating fast pulse pair. And as this whole chain breaks and reconnects, down the middle, we actually get this unstable periodic orbit, which corresponds to the 1D spiral in that thick black line. And so it's really hypothesized then that this bifurcation is due to these rearrangements of the unstable manifold of the slow pulse. And so one of the key assumptions that we're going to be making is that this whole chain of heteroclinic connections is rearranging simultaneously. And so that allows us then to really just consider the case of a slow pulse, or of a single slow pulse and a single fast pulse, rather than dealing with all of these series as we go down the line. So one of the first things we did is we want to give some more numerical evidence that this bifurcation structure is actually correct and that there's actually a heteroclinic bifurcation going on here. So what we did is we computed those 1D spirals as I had previously described, and then we continued it in that parameter epsilon. And what we find is this black continuous curve that as we approach that value of epsilon star, which is indicated by this dashed line, we see that we actually have this this scaling that we would expect from a heteroclinic bifurcation. And so on the right, I'm showing you some of the images along this series, and you can see that as we approach that heteroclinic bifurcation, the slow pulse at the center is propagating for much longer before splitting into those into that like reflected behavior. So I also want to point out that I'm using this epsilon here as this bifurcation parameter, but we can also use any of the other parameters as this main bifurcation parameter as well. We've been using epsilon since that's what's been historically been used, but you can do the same computation with any of those parameters I previously talked about and find that they actually obey the same scaling. And we see that as you would approach that bifurcation point, it obeys this log of mu minus mu star scaling, indicative of that heteroclinic bifurcation. All right, so we're more confident now that there actually is this heteroclinic bifurcation going on. And what we want to be able to do is directly compute that point epsilon star, because we could just continue very close to it, but never actually find it. But that would be really computationally expensive because we'd have to do this continuation until we're certain of where that epsilon star is. So what we really want to do is be able to solve for directly that heteroclinic bifurcation point. And the way we're going to do this is, again, by setting up a pattern to solve for. So if we consider our 1D spiral, the limiting case as we approach that heteroclinic bifurcation is really a slow pulse that comes in from infinity, breaks into the slow fast pulse pair, and they continue on for indefinitely long as well. And so what we're doing then is really computing the heteroclinic connection between the unstable manifold of the slow pulse and this oppositely propagating slow fast pulse pair. And so what we're going to do is this slow fast pulse pair, this oppositely propagating pair, where they actually, we're going to say they live on a manifold that is parameterized by that peak to peak separation. And we're going to directly compute this heteroclinic connection. And so I have this also schematic down the bottom, which is essentially the same as this one up the top, where we have the slow pulse on the left and that slow pulse pair on the right. And so we want to compute this connection here. And so we're going to do so via a truncated boundary value problem. So what we're going to do is we're going to actually start near the slow pulse, but in a small direction or a small distance away in the direction of its unstable manifold. And we want our boundary condition at the end to be perpendicular to the unstable adjoint eigenfunction of that slow pulse pair. And so we do that by setting up this boundary value problem, which we put in the moving frame of the slow pulse and incorporating these boundary conditions directly into this pattern. So to be able to compute this heteroclinic bifurcation point, what we're doing are directly computing this Y-shaped pattern. And also, I should say that this epsilon star, this bifurcation point, this is a free parameter in our system. And because of the dimensions of these unstable manifolds on each side, it only exists for finite values. So we're going to be able to find that epsilon star exactly. All right, so what we want to do then is understand how this bifurcation point depends on those system parameters. So by setting it up, the problem up in using that truncated boundary value problem, we can compute the pattern, and we can also then continue the pattern in the system parameters. And so as we continue system parameters, not only is the location of this epsilon star going to change, but the location of that saddle node bifurcation is also going to change as well. And so we're going to track the location of both of them, because really the ideal conditions that we would want in order to remove these reflections, we would want there to be a high saddle node bifurcation point, because we need these traveling pulses to exist in cardiac tissue because they really organize the contraction of the heart. But we would ideally like there to be a really low epsilon star. So as we change different system parameters, the two of them are going to move together. So the ideal conditions are in this bottom right. But then, for example, in this bottom left, what could happen is that epsilon star stays low, but the saddle node bifurcation bumps in as well. And you get the other combinations on the top as well. So again, the goal is to find conditions with high epsilon saddle node and low epsilon star. And so what I've done here is plot the respective values of epsilon star on the vertical axis and epsilon saddle node on the horizontal axis as we change these different parameters. And these figures in the corners kind of represent the different scenarios that are happening in the different regions of this plot. Furthermore, this gray line represents epsilon star equal to epsilon saddle node. So all of this area up on the top left cannot be obtained. So a couple of things that I want to point out. First, that as we change these system parameters, we see that overall there's a monotonic response between epsilon star and epsilon saddle node, except for one parameter. There's this U4A, which for moderate changes in it actually result in this negative slope. So conditions over here on the bottom right, they are the ideal situation, where we're not really changing that saddle node, but we are greatly reducing that epsilon star. So I'm going to keep track of this U4A once we go to interpret this back in the context of the physiological system. The other thing that I want to point out is that the two conductances, the GCA and the GK, which are in the dark blue and the orange curves, they have a huge influence on the location of both these bifurcation points. And if we look at their slopes, well, they're actually pretty linear. So it's a bit unclear to us if, particularly for these variables, if the influence on epsilon star is actually directly caused by these variables, or if it's more of an indirect effect because the saddle node bifurcation is changing so much to begin with. But those parameters that control the shift in the scale of that potassium channel seem to have more influence on epsilon star than on epsilon saddle node. And so what we can do is also look at the ratio of epsilon star divided by epsilon saddle node, so that lower values of this correspond to the 1D spiral existing for a smaller portion of that traveling wave interval. And so here I'm presenting this as a % of the parameter change so that we can get a little bit of a sense of the sensitivity to the system on these parameters as well. And so again, I want to point out that kind of lower values are better, higher values are worse in our case. And so that U4A seems to be doing the best. And so this analysis also tells us how we can reduce this ratio by increasing and decreasing these different parameters. All right, but I'm going to come back to interpret this physiologically at the end. So the second question we want to then ask is that if we assume the 1D spiral exists, So we are assuming we can't change the location of that heteroclinic bifurcation point. What is the probability that we actually get reflections? Can we control that probability somehow? And so to do that, we're going to look at the spectral stability of this 1D spiral. So remember, we phrase this as an equilibrium solution, which means that we can then find the eigenvalues in the spectra of this linearized operator. And so when we do that, we find that there is a single leading unstable eigenvalue of the point spectrum for this 1D spiral. And that's shown in this figure on the left. So you will see that there are vertically periodic branches. Well, they happen at plus or minus I times omega, which is the angular frequency, because of that periodic nature of the pattern. And the eigenvector that's associated with this unstable eigenvalue, well, this is nice and localized at the core. So what we're going to do then is use the magnitude of this eigenvalue as a measure for how unstable that periodic orbit is, in order to say if it's going to be more or less repelling, so that we know how close to the system we have to get in order to generate a reflection or two. So to first show that this unstable eigenvalue of the 1D spiral actually does measure or give a measure of the probability of reflection, what we've done is repeated that refractory bump experiment as we change all of those different system parameters. So in the vertical axis, what I'm showing you is the difference in the B values that actually generate a reflection. So we change the height, the amplitude of this bump, B, find what is the minimum value that generates reflection behavior, what is the maximum value that generates reflection behavior, and so you're seeing the length of that interval on the vertical axis. And so this directly gives us a measure of the probability of reflections by telling us how many conditions are creating those reflections or how sensitive it is to the conditions. What I'm showing you on the horizontal axis is the value of that unstable eigenvalue, which I'm going to call lambda u. And so what we can see is that there's, for the most part, this nice linear trend where if we increase the eigenvalue, make the system more unstable, we're also less likely to get reflections, as only a smaller interval of those amplitudes will generate those reflections. There are potentially some nonlinear effects going in, especially with GCA, but for the most part, this is a reliable measure for the probability of reflections. So what we can do again is use our continuation methods with this eigenvalue problem in order to see how that unstable eigenvalue changes as we change different system parameters. And so again, I'm showing this as a percent of our parameter change so that we get a sense of how sensitive the system is to these parameters. So the values at the top represent the system being more unstable and the bottom less unstable. So we want our system to be more unstable so that you have to approach the periodic orbit closer in order to generate a reflection. And so what we find that in particular, the potassium conductance, this GK, and this parameter U4B, they really control the stability of this 1D spiral quite well. And the system is pretty sensitive to those two. If we were to increase those two, we're much less likely to get reflections. We're also less likely to get reflections if we decrease GCA, U3A, and U3B to lesser extents. And in particular, a lot of these, like this U3A and U3B, I'm only showing it up to 100% parameter change, but we've continued it much further, and you can get much more changes in those eigenvalues as well. All right, but I want to reinterpret these results in the context of the physiology and see what can we find from here. So we're using the Morris-Lacar model for this problem, one, because it is still relatively simple, but two, because it does have some realistic behaviors in it, and the terms are loosely tied to these physiological behaviors, so we can interpret our results a little bit in the context of this physiology. And so again, I want to remind you that the GCA and GK, they are the maximal conductances that control the strength of those potassium and calcium currents, whereas U3A and U3B, they act to shift the activation curves, and the U4A and U4B act to scale those activation curves. So they change the rate of the activation and the deactivation. So when we were to look at this in the spatially extended tissue, these traveling pulses, in order for them to exist, they require this balance of this calcium and potassium currents in order to create these pulses. And so reflections in particular, then, what they would require is that the calcium current needs to overcome the potassium current at the pulse back to actually send out a counter-propagating wave. And so because of this balance and because of the need for the calcium current to overcome the potassium current, we then expect that these two conductances will heavily influence both the 1D spirals and the pulses. And we already saw a bit of that in that the epsilon saddle node and epsilon star were both heavily dependent on these two parameter values. But what we find is that these other values that control the rate and scaling of the potassium gating variable also control it as well. So remember, our ideal scenario in order to reduce the probability of reflections is that we would likely have a large unstable eigenvalue, and we would like to have a low epsilon star epsilon saddle node ratio. So if we analyze this from the stability point of view, the best conditions that can decrease the stability are to increase GK in U4B and decrease GK in U3A. Those are the ones that have their most sensitive in the system at influencing that stability. In terms of the existence then and changing this ratio, the best conditions to decrease this existence would be, in particular, to moderately increase this value of U4A, because we actually see that there's that negative slope there. And so it's directly impacting epsilon star, but not impacting the ability for traveling waves to propagate. We also do see that it would be able to decrease this existence by changing U4A as well, and U3A and U3B. We also have this heavy influence of GK and GCA, but that impacts both these bifurcation points heavily, so it's unsure what the direct impact on the 1D spiral is from those two. So if we then take this one step further and try and interpret this in terms of what's actually happening, well, the conductances, if we're to increase GK, what this does is strengthen the potassium current. So it means it strengthens the repolarization process. Decreasing GCA, this weakens that depolarization process and weakens that calcium current. So essentially, these are acting exactly as we would expect, that decreasing GCA and strengthening GK means that that pulse cannot escape from the back and create that reflection-like behavior. If we look at the potassium channel gating, what's actually happening, we would want to increase U4A and U4B, which are shown here on the right, and these arrows indicate the direction of increasing the parameter. And as I'm listing here, I've written E or S to indicate that it more directly impacts the existence or the stability or both. But if we're to increase these U4A and U4B, what they actually do is act to U4A, for example, at higher voltages, it acts to reduce the rate of activation. But if we look at some of these lower voltages, it actually increases the rate of activation near the threshold dynamics. So moderate increases in this U4A, what it actually does is act to activate these potassium channels earlier in the action potential cycle, which means so that that repolarization process can happen sooner. And then as you increase it more, as you increase this value more, it actually really dampens the activation at the higher amplitudes as well. And so this is why we think that U4A had that kind of bend, that negative slope behavior, because small increases in it are able to increase the activation at low voltages. But if you increase it too much, you get negative effects because you're really reducing your activation rate at those higher voltages as well. And kind of the same thing goes for if we were to increase U4B, what we do is reduce the deactivation of those channels. So essentially both of these act to adjust the rate of that reactivation process. And then similarly, if we're going to decrease U3A, we actually shift these curves against the arrows, and decrease U3B, again, shift against the arrows. So what both decreasing these does is it acts to activate our potassium channels earlier and deactivate them later. So we are working with this Morse-the-Car model, but we can make some predictions for more general systems and say then that the likelihood of reflections could be reduced by increasing the active duration of those repolarization channels, and also possibly by slowing down the rate of those potassium channels as well. All right, so in summary, our big goal was to understand what conditions lead to and or deter this reflection behavior. And so to understand that, we went with this assumption that the reflections are directly tied to the existence of this 1D spiral and this unstable periodic orbit. And so therefore, to understand the probability that these reflections arise and understand how we can control them, we look at the existence of these reflections and the stability of these reflections by looking at the existence and stability of that 1D spiral. So in order to actually compute these, we computed different spatiotemporal patterns numerically to both compute the 1D spiral directly and also compute that heteroclinic bifurcation point. So some of our outcomes are that we show that there's additional evidence for this heteroclinic bifurcation structure in the Morse-the-Car model that actually generates these reflection behaviors. And we found that these reflections may be best deterred by increasing the activation time of those repolarization channels or by altering those rates as well. So a third outcome that we actually had that I didn't talk about here for the interest of time is that we interpreted our results under the concepts of the excitability type of the local reaction dynamics. And so it was hypothesized by Ermentrout and Rinzel that these reflections are more robust in systems that have true threshold type behavior in their reaction kinetics, so type 1, and interpreting our results under those contexts, we find that this hypothesis is true, that reflections are more robust in type 1 excitable systems. So I didn't show you those results here, but I'm happy to talk about them if you have other questions. And so we do have still many unanswered questions. So really the long-term goal is that we want to be able to expand this analysis to a more biophysically realistic model and eventually be able to incorporate some antiarrhythmic drug therapies to understand if and how they're influencing the probability of reflection-mediated arrhythmias. And we want to do this because some antiarrhythmic drugs have been shown to actually reduce the probability of arrhythmia, whereas some actually, in some cases, promote arrhythmias. And so we'd want to understand if it's related to this at all. And additionally, we've provided more numerical evidence for this heteroclinic bifurcation, but we still need to rigorously prove the form of this heteroclinic bifurcation. So with that, I'll stop there. And I'd like to thank all of you for being here today. And thank you again for the invitation to be here.